morning, everyone. My name is Steve. Welcome to our webinar for today, Touchpad Programming in HMI Works using C language. This will be the third and last part of the series, where we will create an application that can scale process value, change widget property at runtime, accept user input and save parameter to memory. We will have an overview of the TPD and VPD series of touchpads, some features of HMIWorks, and a complete example in C language. We will scale value from 4 to 20 milliamp to temperature, change colors of labels, and disable click property of push button. ICP DAS was established in 1993. The headquarters is located in Hsinchu, Taiwan. ICP DAS USA was launched in 2001 to support the North and South American markets. We have over 200 R&D engineers, and we work closely with them to add new features to our products, develop new products, and to support our customers. Most of our products are RoHS compliant, which means they are lab-free. We also have our ISO 9001 certification. The touchpads must be programmed with the HMI. This ICP DAS USA has two types of touchpads: the TPD series for home and building automation, and the VPD series for industrial applications. They are cost-effective solutions that can be used as HMI and controller. The TPD series have wall boxes for easier mounting, and the VPD series have a IP65 waterproof front panel. The size are from 2.8 to 7 inches, and there are options for serial and Ethernet communications, including with power over Ethernet. The touchpad must be programmed with HMIWorks software or IDE and can be downloaded free of charge from our website. HMIWorks allows for programming in C language and ladder diagram. In this webinar, we will focus on programming in C. It has widget and a graphic library to create user-friendly HMIs. The touchpads can communicate with Modbus protocol and can act as master or slave device. They also have the DCON protocol, and user can program their own protocol also. For this webinar, we will use a TPD to ADU, which is a touchpad with a screen of 2.8 inches. We will be reading 4 analog inputs from a Modbus slave simulator. First of all, we need to create a connection for Modbus RTU and a device with a parameter needed, like we did in the previous webinar. In the workspace, we have the connection and the text of the PLC device that we can use in the project. For this demo, we will only use 4 analog input tags. We rename the frame to scaling We use one picture box for the logo and 3 text boxes for the name of the screen, also 2 columns. Read values and scale values. To show the value, we use 8 labels. For ease of programming, we can change the name of the labels in the inspector window on the right side. This way, when we are coding and the widget are easier to identify throughout the code. As we can see in the example, we change the name of the labels to read value. HMIWorks will automatically add the ID to the name. So the first label will be read value 8. The second will be read value 9, and so on. Make sure the timer is enabled and create an on execute. For the timer name, we use tmrScaling. That is another way of naming the widgets, where the first letter indicate the type of widget that is being used. Before going on the programming, let's explain why we need the scaling functions. Normally, temperature sensors may have a 40 to 20 milliamp output, representing temperature range from 0 to 100 degrees Celsius. If we use a ICP DAS remote I/O module, it will use 4,000 to 20,000 as the raw values. That 4,000 representing 0 degree and 20,000 representing 100 degree. We will need to use a math equation y equal mx plus b to calculate the scale values. After we solve the function, the result of ratio will be equal to 0.00625. We'll use this number for the functions. B will be negative 25 after solving the equations. For the code, we will define 8 strings to show the values in the labels on the screen. We need 4 floating numbers variables to store the value of analog inputs. And the scaling function will simply return a float number. That is the result of the math expression we just calculated. In the event handler of the timer, we first calculate the scale value by passing the value of input register to the function scale temperature. Then we will print the value of input register to the label in order to show it on the screen with the US printf on function on line 39. In common C language, you can use sprintf function also with a %f parameters to print floating numbers. But in HMIWorks, you need to use float to string function, like the one on line 44. Then we use label text set function to set the string to the labels on line 49. Instead of showing only the values, we can also use a function to check the limits of scale values and return a color to identify if they are accepted in the accepted range or not. The function CheckLimits will compare if the scale value is below 10, then it will return blue. If the value is above 90, it will return red. Otherwise, it will return a white color. You can search for RGB hex color codes if you want to know the color coding. Shown below only the basic colors. With the CheckLimits function ready, you can finish the timer event handler. After setting the text to the labels, we will use the canvas fill color set function and CheckLimits function to get the color. Once the color is set, we use rigid paint function to actually change the color. Here we can see the screen when all the values are in range from the first picture, and the second screen where the first value is below 10. That's why it becomes a blue color, and the last value is above 90, so it turns to red. In the CheckLimit functions, we use the value 10 and 90, and those are fixed in the code. If the user wants to change the limit, let's say 15 and 85, we need to create a configuration screen. We will start with putting a TextPush button on the scaling screen. That will take us to the configuration screen. We could use a picture or hotspot or just label. In this case, we have a screwdriver logo here. This is just another way to achieve the same result. We rename the button to PB configuration and create an on-click event handler. We also use an object list to show a graphic. For example, the tools to indicate configuration. Be cautious on using the text push button object list. If you only put one image, it will only turn right when you click on the button. Make sure to put a second image for the click state. You could use a different image for the object list, or in another option is, in our case, we will use the same image twice. Next, we will create a new configuration screen. Put the logo and text boxes. We will add text push buttons with plus and minus sign to adjust to the values of the limit. The name for the selected minus sign is TPB minus, and labels is low limit. There is also the button to get back to the scaling screen, like the exit door. We can preview the graphic on the bottom left. You can see the door with the exit arrow. We will use it as exiting screen back to scaling screen. Be Before starting the code, we'll create 3 new virtual tags: band, high limit, and low limit. High limit will have a default value of 90. Low limit will have a default value of 10. And those will be the limit we'll use in the CheckLimits function. Band is just another variable to make sure the high limit is always 20 greater than the low limit. For the programming, the scaling screen only need to change the CheckLimits function to use the text instead of value 10 and 90. And we need to add the code in order to change the configuration screen. For the configuration screen, we need to create 2 strings to show the values in the labels. When we press the minus button for the low limit, we subtract 1 from the current value. If the result is -1, we set it back to 0. We then show the values in the label. As you see from the 9.4 to 9.10, this is what happened to the minus button. For the plus button, from 9.14 to 9.20, when we press the plus button, we will add 1 to it, and then check the low limit is 20 lower than the high limit. If not, we'll keep low limit at high limit. Similar for the high limit, when pressing the minus, we will check if it is 20 higher than the low limit. And when pressing the plus sign, we will let it increase until 100. Finally, we will add the push button code to go back to the scaling screen. The first screen here shows all values are in normal range with the original limit of 10 and 90. We then change the low and high limit to 15 and 80, as you see from the middle picture. Once the limit is set, we go back to the scaling screen, and you can see one of the box turn red because the values exceed 80 and it reached the high limit. If we want to avoid that anyone can change the limit, we can control the access to the configuration screen with a password. We will add a button to go to the screen to enter the password. We also need to set the enable property of the TPP configuration to false. This way, clicking on the button will not show the configuration screen unless the password is entered and the button is enabled again. Finally, we add a second time to check if the user is logged in. After 60 seconds, it will automatically log out. So now we will add 2 more new tags. Logged in to check if the password has been entered. The default value will be set to 0, and password will hold the actual value of the password. The default value is 1, 2, 3, 4. The new code to add on the scaling screen is for the button to go to password screen. We also need to add a on-show event handler for the scaling frame. It will be the code execute every time when the screen is shown. Here we check the login tag is 1. In this case, we enable the button to go to configuration screen. Otherwise, we disable the button. Timer will check whether the user is logged in or logged out after 60 seconds. We create a counter, check login. Every time the timer executes, we increment the counter if the user is logged in. When counter reaches 60, we set the tag login to 0, which is the same as logging out, and disable button to go to the configuration screen. For the configuration screen, we do not need any modification. We need to create a screen to enter the password. In this case, we will enter the password digit by digit. We use 4 labels widget for the digits and 6 text push buttons for up and down arrows. For the log in and log out buttons, we will use a text push buttons too. But this time we'll write a text message. If we use the text as image, HMIWorks will automatically create an object list with the text as an image. Another property we can change is the color that the buttons show when pressed. It is red by default, but in this demo we change it to white, which is 0xFFFFFF. Now we'll add a checkbox to show a gray key when the user is logged in and yellow key when it's logged out. The timer is used to print the asterisk character to the labels after 2 seconds. Then a digit has been entered. To hide the password, we create 4 variables to hold the 4 digits and 4 strings to print digit to labels. The check show asterisk will be set to 1 every time a digit is entered. It will know what to print an asterisk to the labels when the timer executes. When the screen is shown, all the digits are set to 0, and the correct key is shown depending on the state of login tag. The exit button simply takes the user back to the scaling screen. The ShowAsterisk timer will check if the check ShowAsterisk variable is set to 1, so it can print asterisk to the labels to hide the enter the password. For the up button, we simply increment the variable of digit. When it reaches 10, we roll back to 0. Then we'll print the values to string and show it on screen, and set ShowAsterisk equal to 1. For the down button, it's really similar to the up button. We just subtract 1 from the digit and roll back to 9. Finally, we have a login and logout button. Login will calculate the value of power multiplied each digit with an appropriate multiple of 10. PWD is then compared to the value of password text, and if they match, login text will be reset to 1 and the yellow key will show. Logout will set login text to 0 and show the gray key. Here we can see what happened after entering the correct password by pressing login. The key will turn to yellow after login. And we can going back to sharing screen while login will allow the user to go to configuration screen. We now have low limit and high limit tags that have default value of 10 and 90. It can be changed by the user also. If the touchpad is shut off, the changes will be lost. The limit text will use the default value when the touchpad is powered back on again. For the password, we have the same case, where the default value is 1234, and it will be useful to have a way to change the password. In both cases, we can use the memory of the touchpad to store user parameters so that they don't lose the information when the touchpad is powered off. HMI Works provides function to read and write the memory. We'll use a label to check the value that is being read for the first time from the memory. The label is set to visible, and afterward we can set the property to false to hide the label, so that we don't need to delete it from the screen, and it can use for other tests if needed. To start using the memory, we read a value at position 255 with the function HMI user parameters get and store it in a variable tmp. We then print the value to the string and show it on screen. Here we see the code can comment out, because we only need to do this while developing. To make sure what value is being read, we can see that the unused memory will return a value of 0. With the value of tmp, we can check if it's 0 or 1. If it is 0, which means there's unused memory unavailable, we can store the value of we can store the low limit value and high limit and password text to the memory, and we write a 1 to the position 255 so that in future we can read back the value of 1 in the future. When we read a value of 1, we will read those values from memory and then set the text to the value being read. This way we can recover any settings the user has changed. On the configuration screen, we only need to put a Save button so that we can store the change the limit. The user memory has limited cycle of read or write, so don't use this function to write to memory in loops or call it frequently. Otherwise, the memory will be full and it can be damaged. For the configuration code, we need to add the instruction to write low limit and high limit text to memory when the Save button is pressed. When the screen is shown, we also need to print the current value of the text to the labels. On the password screen, we add a button to set a new password. It will store the current password displayed when the user is logged in. So the user needs to enter the old password first, log in, and then change to the new password, and then press Set New. The code for the Set New button will simply calculate the new password and store the password to the user memory. To test the new settings, the user can change the parameter and store to memory, power off the touchpad, and then turn it back on to check if the parameter is correct. In today's webinar, we have learned how to read AI and DI via Modbus RTU using C language API, how to read, write using connection and device setup, use of text are available for the touchpad project, also how to create scaling function, change feature properties at runtime, read user input and store values to memory using C language. We have finished our webinar for today. Please feel free to ask any question you may have. Follow us on Facebook, Twitter, LinkedIn, and Google+ to get the most updated information in industrial automation. If you want to see this webinar again, you can go to our website and we will upload the webinar after it's finished. I don't see any questions, so if you have any question, you can call us or send us an email. Thank you all for attending today's webinar. See you next month.